Hello there, and welcome to the Sleepy Space Channel. If you wait long enough, the universe ends. Not in fire, and not all at once, but in a slow fading, as the last stars burn out, the galaxies drift apart, and even the black holes evaporate into the dark. What remains is called the long cold, a stillness so complete it is almost hard to call an ending at all. Tonight we will walk the whole length of that road, from the bright sky we live under now, all the way to the final dark, and ask the quietest question of all, whether even that is truly the end, or whether something still waits beyond it. If you find these slow journeys through space worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next couple of hours, none of this is yours to carry. Settle in. Let your shoulders soften. Let your breathing slow and lengthen. Let the day drift away from you, out past the stars and into the long, calm dark. Let's begin. Part 1. The universe as it is now. Everything that exists is slowly coming to an end. The stars overhead, the galaxies beyond them, the matter in your own hands, the empty space between the worlds. All of it is moving, quietly and without hurry, toward a single distant condition that the universe has been approaching since its first moment. It is a strange thing to sit with, and a sobering one, but it is also one of the most settled conclusions in all of science. The universe had a beginning. It will have an end. And tonight, slowly and gently, we are going to walk the entire length of the road between them. We begin where we are. We live in what astronomers call the age of stars, the long, bright chapter in which the universe is full of light. There are hundreds of billions of galaxies scattered across the observable cosmos, and each of those galaxies holds tens or hundreds of billions of stars. New stars are still igniting out of clouds of gas and dust, the way they have for billions of years. To us, this seems like the natural and permanent condition of the universe. A sky full of stars feels eternal. It is not. The age of stars is only a brief early flowering, a thin band of brightness near the very start of a story that runs on almost without end. Everything that will happen tonight, every era we are about to visit, lies in the future of this lit and crowded present. And when we reach the far end of the timeline, you will be able to look back and see that all of human history, every life that has ever been lived, sits in the first soft instant of the morning of the cosmos. The universe is a little under 14 billion years old. That number already feels beyond holding. It is far longer than the age of the Earth, far longer than the age of the Sun, far longer than the span any living thing has known. And yet, measured against what lies ahead, 14 billion years is almost nothing. It is the opening sentence of a book whose pages run on for spans we can barely write down. The eras we are about to travel through are longer than this one, by amounts so large that the entire age of stars becomes a single bright line at the beginning of the timeline. To make sense of the journey, it helps to picture the present universe clearly. The galaxies are not scattered at random. They gather into groups and clusters, and those clusters string themselves along enormous filaments, like beads of light strung on invisible threads. Between the threads lie immense and nearly empty regions, the cosmic voids, where almost nothing exists at all. This arrangement, the filaments and the voids together, is called the cosmic web, and it is the largest pattern in nature, the framework on which all the light of the universe is hung. Within that web, our own galaxy turns slowly in the dark. The Milky Way is a barred spiral, a flattened wheel of several 100 billion stars, with long curving arms wound around a bright central bulge. Our sun is one ordinary star, far out in one of those arms, circling the center once every couple of 100 million years. It has made that circuit many times already, and it will make several more before its own story ends. The sun itself gives us a small preview of the long fading to come. It is a middle-aged star now, roughly halfway through its life, burning steadily and warmly as it has for billions of years. But in something like 5 billion years, it will begin to change. It will swell into a red giant, grow large enough to swallow the inner planets, and then gently shed its outer layers into space, leaving behind only its exposed core, a small dense ember called a white dwarf. The sun will not explode. It will simply let go of its outer self and settle into a long, slow cooling. What happens to one star in 5 billion years is, in miniature, what happens to the whole universe across spans far longer. There is one more thing to notice about the present before we move on. The matter you are made of was not here at the beginning. The universe started with only the lightest elements, hydrogen and helium, and almost nothing else. Every heavier atom, the carbon in your cells, the oxygen you breathe, the iron in your blood, was forged inside earlier generations of stars and scattered into space when those stars died. We are built from the ash of stars that lived and ended long before the sun was born. The universe had to make and unmake several generations of stars simply to assemble the ingredients of a single living world. It is worth holding, for a moment, just how much there is in this lit chapter of the cosmos. The observable universe, the part of it whose light has had time to reach us, is something like 90 billion light-years across, and it is filled with those hundreds of billions of galaxies, each a turning city of stars. The number of stars within reach of our telescopes is larger than the number of grains of sand on every beach on Earth by a wide margin. And every one of those stars is, right now, in this same bright chapter, burning its fuel and pouring light into the dark. We live at a time when the universe is as full and as luminous as it will ever be. There is a quiet privilege in that timing. If we had arisen far earlier, the heavier elements needed to make worlds and living things would not yet have been forged. If we had arisen far later, the sky would already be emptying, the distant galaxies already slipping beyond reach, the evidence of the universe's beginning already faded from view. Instead, we find ourselves here, in the long, bright middle, when the stars still shine and the wider universe is still open to be seen. It is a good time to be looking outward, and a good time, on a calm night, to follow the whole story forward to its end. There is a useful way to picture our place in time. Imagine the whole future of the universe drawn out as a single long line, with every era marked along it to scale. The age of stars, the chapter we live in, would sit crowded against the very left edge, so near the beginning that you would need to magnify that edge enormously just to find ourselves within it. Nearly the entire line, almost all of the length of time, would lie in the eras still to come, the cooling and the dark and the long cold beyond. We are not in the middle of the story. We are in its opening words, reading by the light of stars that have only just begun to shine. So this is where we stand. We live in the lit and crowded middle of things, in a universe still making stars, still turning, still warm. It is easy to mistake this for how things always are and always will be. But the brightness around us is early, and it is temporary, and the road ahead leads slowly and certainly away from it. The cosmos is already moving, very quietly, toward its own long rest. And so we begin the walk forward, into the far future of everything, one era at a time, starting with a change so gradual that no one alive will ever feel it. The brightest hour of the universe, it turns out, is already behind us. Part 2. The brightest hour behind us. The universe was once far brighter than it is today. Long before the sun existed, in the first few billion years after the beginning, stars were forming at a tremendous rate, far faster than they form now. The galaxies of that early age blazed with young, hot, massive stars, and the cosmos was lit more fiercely than it has ever been since. If you could have stood in a galaxy then, the sky would have been crowded with brilliant blue stars, and the rate of new star birth would have been many times what we see around us today. That peak is over. The universe passed its brightest hour billions of years ago, and ever since, the rate at which new stars form has been slowly declining. It is a gentle decline, not a collapse, far too gradual to notice across a human lifetime or even across the whole history of our species. But measured across cosmic time, the trend is clear and steady. The cosmos has crossed the high point of its own light and is now easing, very slowly, into a long dimming. The reason is simple enough. Stars form from gas, and the supply of fresh, usable gas is not endless. Each generation of stars draws down the available material, and a portion of that material is locked away forever in remnants that never give it back. Slowly, across the galaxies, the reservoir of gas that can still collapse into new stars is running low. There is less raw material for star birth now than there was in the early universe, and there will be less still in the ages to come. This means the universe ahead of us is one of fewer and fewer new stars. The grand era of starbirth is not something we are heading toward. It is something we are already leaving behind. We happen to live a little after the peak, in the long, gradual decline that follows it, while the sky is still full but no longer filling as quickly as it once did. It is worth pausing on how unhurried all of this is. The decline in star formation unfolds over billions of years. Our sun will live out its entire remaining life, swell into a red giant and fade into a white dwarf, all while the universe is still comfortably within the age of stars. Whole civilizations could rise and fall on countless worlds, across spans in which the overall brightness of the cosmos barely shifts. The end of the universe is not a fast thing. It is the slowest process there is, and that slowness is itself a kind of mercy. Still, the direction is set. If you could watch the universe from outside and speed up time enormously, you would see the galaxies gradually shift in color. The fierce blue light of the early cosmos would give way, age by age, to softer yellows, then to oranges, then to reds, as the brightest and shortest-lived stars burned out and were not replaced. The universe does not go dark all at once. It reddens. It cools. It quiets. The change is so gentle that, from the inside, no single generation would ever see it happen. There is a balance at work here that is worth understanding, because it shapes everything that follows. The most massive stars are the brightest and the most spectacular, but they are also the most wasteful. They burn through their fuel in only a few million years, and then die in tremendous outbursts, the explosions we call supernovae. The smallest stars do the opposite. They burn slowly, frugally, sipping their fuel across spans of trillions of years. So as the gas runs down and starbirth slows, the universe shifts away from the brilliant, short-lived stars and toward the dim, patient, long-lived ones. The future favors the small and the steady. The peak of cosmic starbirth is sometimes called the cosmic noon, the high point of the universe's light, and it lies many billions of years in our past. In that era, the galaxies were forming stars many times faster than they do today, blazing with the light of countless young suns. Since then, the rate has been falling steadily, not because anything has gone wrong, but simply because the easiest, densest gas has already been used. What remains is thinner and harder to gather, and so each new age makes a few less stars than the age before it. The universe is not failing. It is only spending down a fortune it accumulated near the beginning. You can see the long color of this change if you imagine the galaxies aging. A young galaxy, full of massive blue stars, shines with a hot blue-white light. As those massive stars die first, in only millions of years, the galaxy's light shifts toward the yellow of stars like the sun, and then, over billions of years, toward the orange and red of cooler, longer-lived stars. An old galaxy glows redder than a young one, simply because its brightest, bluest members have already burned out. The reddening of the galaxies is the visible signature of the universe growing older, the slow warming of the cosmic light toward the color of embers. None of this dimming is anything a single observer could ever watch happen. The decline in star birth unfolds across billions of years, far slower than the rise and fall of mountains, far slower than the drift of continents. A civilization could arise, flourish for ages, and pass away, and the overall brightness of its galaxy would scarcely change in all that time. The fading of the cosmos is real, and its direction is fixed, but it is gentle beyond any human reckoning, a change measured not in years or lifetimes, but in the slow turning of cosmic ages, each one longer than all of recorded history, many times over. This is the quiet logic that carries us into the next era. The bright stars are a phase, a flare near the beginning. The lasting inhabitants of the universe will be the faint red embers that burn for almost unimaginable lengths of time. But before we follow those embers into their long reign, there is a larger change to understand, one that does not touch the stars themselves at all, but the space between the galaxies. For while the cosmos is slowly dimming from within, it is also, on the very largest scale, quietly coming apart. The galaxies are drawing away from one another, and the sky itself is beginning a long goodbye. Part 3. The first long goodbye. The single most important fact about the future of the universe is that it is expanding. Space itself is stretching, growing larger with every passing moment, carrying the distant galaxies away from one another, like markings on the surface of a balloon being slowly inflated. This is not the galaxies flying outward through space. It is space itself growing, opening new distance everywhere at once. And for reasons we are still working to understand, that expansion is not slowing down. It is speeding up. The cause is given a name, dark energy, though the name is more a label for our uncertainty than a true explanation. Dark energy appears to be a faint, even pressure built into empty space itself, a gentle outward push that exists everywhere, in every region of the cosmos. Where there is more empty space, there is more of this push. And because the universe is constantly making more empty space as it expands, the outward pressure grows and the expansion accelerates. The more the universe stretches, the faster it stretches still. Across ordinary spans of time, this changes very little that we can see. But across the long future, it changes everything about the sky. As the expansion accelerates, the most distant galaxies are carried away from us faster and faster. Their light, traveling toward us across the widening gulf, is stretched to longer and longer wavelengths, reddened and dimmed by the growing distance. And eventually, for the most distant galaxies, the space between us grows so quickly that their light can no longer cross it at all. They pass beyond a kind of horizon, a boundary past which nothing can ever reach us again. One by one, across enormous lengths of time, the distant galaxies will redden, dim, and slip silently over that horizon, vanishing from view forever. They will not be destroyed. They will simply be carried so far away, so quickly, that their light can never again find us. The universe will not grow darker because its galaxies die. It will grow darker on the largest scale because its galaxies recede beyond reach, retreating into a distance that swallows their light. It is worth understanding what expansion does and does not pull apart, because this is where the long future first touches things close to home. Expansion does not tear apart anything held together by its own gravity. Planets stay bound to their stars. Stars stay bound within their galaxies. Galaxies that are gravitationally tied to one another stay tied. The stretching of space only wins out across the enormous, nearly empty distances between galaxies that are not bound together. There, where gravity is too weak to hold, the growing space carries everything apart. So the things near us are safe from the expansion. The sun will not be pulled from the Milky Way. The Earth, while it lasts, will not be torn from the sun. What recedes is the wider universe, the countless galaxies beyond our own small gravitational neighborhood. Those are the lights that will, across the long future, withdraw into the dark, one after another, until the cosmos beyond our local region appears empty. There is something quietly profound in this. The afterglow of the universe's beginning, the faint radiation that fills all of space and tells us how the cosmos began, will also fade and stretch beyond detection as the expansion continues. A civilization arising in the far future, with no galaxies visible beyond its own and no afterglow left to find, might look out at an apparently small and empty universe and never know that it had once been full, that there had ever been a beginning at all. The evidence will have receded over the horizon. We are fortunate, in a way, to be living now, while the universe still wears its history openly across the sky. We learn that the expansion is accelerating by watching distant exploding stars, certain stellar deaths that always shine with nearly the same true brightness. By comparing how bright they truly are with how bright they appear, astronomers can measure how far away they lie, and by reading the stretching of their light, how fast they are receding. What that comparison revealed was unexpected. The most distant of these explosions are dimmer, and therefore farther than they would be if the expansion was simply coasting or slowing. The universe is not merely growing, it is growing faster with time, pushed outward by the faint pressure we have named dark energy. It is strange to realize how much of the universe this pressure makes up. By the accounting of mass and energy, dark energy appears to be the largest single component of the cosmos, larger than all the matter, both ordinary and dark, put together. And yet within any small region, like a room or a world or a solar system, its effect is far too weak to feel overwhelmed completely by ordinary gravity. It is only across the enormous, nearly empty gulfs between galaxies that this gentle outward pressure wins, and there, given time, it shapes the entire future of the sky. The largest force in the universe is also the quietest. It can be hard to accept that space itself can grow, since nothing in ordinary life behaves that way. But the galaxies are not moving outward through some fixed and empty stage. The stage itself is stretching, and the galaxies are simply carried along with it, like marks drawn on a sheet that is slowly being pulled wider in every direction at once. The further apart two marks already are, the faster the growing sheet carries them apart, which is why the most distant galaxies recede the fastest. This is not motion in the usual sense, and nothing here is outrunning light. It is space, quietly and everywhere, making more of itself. For us, though, the emptying of the distant sky is not a loss to mourn, but a slow settling to understand. The universe is not being broken. It is spreading out, opening, giving every island of light more and more room around it. The galaxies are not falling. They are drifting apart, gently and without end. And as the wider sky recedes, our attention is drawn inward, toward the one small gathering of galaxies that will not recede, the handful that are bound to us by gravity and will travel with us into the future. For while the distant universe withdraws, something is also happening much closer to home. Our own galaxy is not going to remain alone, and it is not going to remain as it is. Part 4. The sky becomes one galaxy. Our galaxy belongs to a small gravitational family. The Milky Way is the second largest member of a loose gathering of galaxies called the Local Group, a collection of dozens of galaxies bound together by their mutual gravity and traveling through the cosmos as one extended neighborhood. The largest member is the great spiral galaxy Andromeda, somewhat bigger than the Milky Way and presently a little over 2 million light-years away. Around the two giants orbit dozens of smaller galaxies, faint companions caught in the same gravitational web. Because the Local Group is bound by gravity, it will not be carried apart by the expansion of space. While the rest of the universe recedes beyond the horizon, this small family stays together. But staying together does not mean staying unchanged. The galaxies of the Local Group are slowly falling toward one another, drawn inward by the same gravity that binds them. And the two largest, the Milky Way and Andromeda, are approaching each other directly, closing the distance between them across the next several billion years. In something like 4 to 5 billion years, the two great spirals will meet. It will not be a collision in the ordinary sense, because the stars within galaxies are so widely separated that almost none of them will actually strike one another. Instead, the two galaxies will pass through each other, their gravity tearing their graceful spiral arms into long streamers of stars and gas. They will swing apart, slow, and fall back together, again and again, until over a span of further billions of years, they merge completely into a single, larger galaxy. Astronomers sometimes give this future galaxy a blended name, Milkomeda, the union of the two. The merged galaxy will not be a spiral. The long, ordered arms of the Milky Way and Andromeda will be scrambled by the encounter, their stars flung onto new and tangled paths. What settles out, after the dust of the merger clears across billions of years, will be a smooth, rounded, elliptical galaxy, a featureless cloud of stars without arms or disk, growing slowly redder as its brightest stars age and die and fewer new ones form to replace them. By the time this happens, the Sun will likely be near the end of its own life, fading toward its white dwarf future, and the Earth, if it still exists at all, will long since have become uninhabitable. So no one on our world will witness the merger. But the event itself is written into the motions we can already measure. Andromeda's approach is observed, its path traced. The merger is not a possibility. It is a future already in motion, unfolding so slowly that it will take billions of years to complete. Now place the two changes side by side, the merger and the expansion, and you can see the shape of the sky in the far future. The distant galaxies are receding beyond the horizon, withdrawing one by one into the dark. The nearby galaxies, the Local Group, are falling together into a single merged elliptical. So the end state is clear. After enough time has passed, an observer in our region of space would see only one galaxy, the merged remains of the Local Group, surrounded by an apparently empty and lightless cosmos. The rest of the universe would have vanished over the horizon, beyond any telescope, beyond any reach. It is a strange and quiet picture. One island of stars, alone in the dark, with nothing visible beyond it. To us, who can still see a sky full of galaxies, that future seems lonely. But the loneliness is only in the seeing. The merged galaxy would still be full of stars, still turning, still home to whatever might live within it. It would simply have lost sight of the wider universe, the way a traveler far out on a calm ocean loses sight of every shore. The water is still there. The world is still there. It has only moved beyond the edge of what can be seen. The approach of Andromeda is something we can already watch. It is one of the few large galaxies moving toward us rather than away. Its light shifted slightly toward the blue by its approach, falling through the gulf between us at a steady pace. Far in the future, as it draws near, it would grow from a faint smudge in the night sky into a great spiral, spanning a wide arc overhead, brightening across millions of years until it dominated the darkness. Any eyes that existed then would see two galaxies slowly leaning toward each other across the sky in the long prelude to their meeting. When the two finally passed through each other, the encounter would unfold across a span so long that no single moment could capture it. The stars themselves, separated by light years, would almost never collide. Space within a galaxy is mostly empty, and the two great wheels would interpenetrate like two clouds of fireflies passing through each other in the dark. But their gravity would tear at their shapes, drawing out long streaming tails of stars and gas, flinging some stars far out into intergalactic space and pulling others into new and tangled paths. Across billions of years of this slow gravitational dance, the ordered spirals would dissolve, and from the wreckage, a single rounded galaxy would slowly form. It is worth remembering that the merged galaxy, for all the upheaval of its making, would still be a calm and ordinary place to live. The stars within it would go on circling its center much as they do now, and any worlds among them would feel nothing of the ancient collision that shaped their galaxy, just as we feel nothing of the mergers that helped build the Milky Way long ago. The grand events of the cosmos, however violent they sound when named, unfold so slowly and across such enormous distances that from inside they are quiet beyond imagining. A galaxy can be torn and remade and never disturb a single sunset on a single world. And so the universe enters its long Middle Age as a scattering of isolated islands, each one a galaxy or a merged group of galaxies, each one cut off from the others by an ever-widening dark. Inside each island, the stars go on shining for now. But even within those islands, the light is on a timer. The gas is running down. The brightest stars are dying and not being replaced. And so we turn now from the great motions of the galaxies to the fate of the stars themselves, and to the slow approach of a moment that will come to every galaxy in time, the birth of its very last star. Part 5. The last stars will be born. Stars are born from gas. A cloud of hydrogen drifting in a galaxy, cold and thin, can begin to collapse under its own gravity, drawing inward, growing denser and hotter at its center, until the core becomes hot enough to ignite and a new star begins to shine. This process has been repeating across the universe for billions of years, and it is the engine that keeps the cosmos lit. But it depends entirely on a supply of gas that can still collapse, and that supply is finite. Every time a star forms, some of the galaxy's gas is converted into the body of the star, and a portion of that material is locked away permanently. The smallest, longest-lived stars hold on to their matter for almost unimaginable spans. The remnants left behind by dying stars, the white dwarfs and neutron stars and black holes, keep much of their material sealed away forever, never returning it to the clouds from which new stars could form. So with each generation, the reservoir of fresh, star-making gas shrinks a little further. The galaxy is spending a savings it cannot fully replenish. Across enormous lengths of time, this drawing down has a clear conclusion. The gas grows too thin and too spread out to collapse into new stars. Star formation slows, and then finally stops. There will come a time, in every galaxy, when the last cloud capable of making a star gives birth to its final one, and after that, no new stars are ever born there again. The galaxy must then live out the rest of its existence on the stars it already has, and on the slowly cooling remnants they leave behind. It is thought that ordinary star formation will largely come to an end across the universe within something like 100 trillion years. That number is hard to hold. The universe is presently about 14 billion years old, and 100 trillion years is many thousands of times longer than that entire history. And yet, against the eras still to come, even 100 trillion years is only the closing of the first chapter. The age of stars is long by every human measure, and brief by every cosmic one. The last stars to form will not be the brilliant giants that light the universe now. Those massive stars are the first to die, burning through their fuel in mere millions of years. By the time star formation is winding down, the gas that remains will mostly assemble into the smallest kind of star, the red dwarf. These are dim, cool, modest stars, far less massive than the Sun, and they have a remarkable property. They burn their fuel so slowly and so completely that they can keep shining for trillions of years, far longer than any larger star. So the final generation of stars in the universe will be a generation of small red embers scattered through galaxies that have otherwise gone quiet. There will be no more blue giants, no more brilliant clusters of newborn suns, no more of the fierce light that marked the early cosmos. The galaxies will hold only their aging populations of small, faint, long-lived stars, glowing softly in reds and dim oranges, with the dark growing between them. If you could stand in such a galaxy, late in the age of stars, the sky would look very different from ours. It would be dimmer, redder, sparser. The brilliant stars we know would be long gone, their light extinguished an eternity before. What remained would be a quiet scattering of cool red points, each one shining steadily, each one with an enormous span of life still ahead of it. The galaxy would not be dead. It would be old and dim and patient, settling into the longest and quietest part of the age of stars. The amount of matter locked away with each generation of stars is the quiet engine of this whole decline. When a star like the Sun dies, it returns some of its gas to space, but it keeps a portion sealed forever in its white dwarf core. When a massive star dies, it scatters much of itself, but locks away a neutron star or a black hole. The smallest stars hold on to nearly all their matter for trillions of years. With every cycle of birth and death, a little more of the galaxy's gas is taken out of circulation, sealed in remnants that will never again collapse into a new star. The reservoir does not refill. It only ever drains. There is also a subtler limit at work. New stars form most easily from gas that has already been enriched by earlier generations, seeded with the heavier elements that help a cloud cool and collapse. But the supply of fresh gas falling into galaxies from intergalactic space slows over cosmic time as the universe spreads out and the easy fuel is used up. Deprived of new material, the galaxies must make do with what they hold, and what they hold steadily diminishes. So, star formation does not stop in a single moment. It tapers across enormous spans, fewer and fewer new stars in each passing age, until the very last cloud capable of collapse gives up its final star. the last star to form in a given galaxy will pass without ceremony. It will be a small, dim red dwarf, no different from countless others, condensing out of the final wisp of gas thin enough to still collapse. Nothing will mark it as the last. Only across an enormous span afterward, when no new star follows it and the gas has fallen silent for good, would the title become clear. The end of starbirth is not an event but an absence, the quiet failure of any new cloud to ever again gather itself into light, noticed only by the deepening of a dark that no fresh star arrives to break. This is the universe shifting, finally and fully, from the brilliant and brief to the faint and enduring. The grand fireworks are over. What remains is a long, low, steady glow, the embers of starbirth burning down toward their close. And these embers, the red dwarfs, are about to inherit the cosmos for a reign so long that everything that came before it, all of cosmic history up to this point, will seem like a single hurried morning by comparison. We turn now to the long red afternoon of the universe, the age that belongs entirely to the smallest stars. Part 6. The long reign of the red dwarfs. For a span far longer than everything that has come before, the universe will belong to its smallest stars. The red dwarfs, the dim and frugal survivors of the age of starbirth, will outlast every other kind of star by an enormous margin. To understand the far future, you have to understand these small stars, because for an immense stretch of time, they are nearly all that will be left shining. A red dwarf is a star much smaller and cooler than the Sun, sometimes only a fraction of its mass. It does not burn brightly, and from a distance it gives off a modest reddish light. But what it lacks in brilliance, it more than makes up for in patience. A red dwarf is stirred all the way through by slow internal currents, mixing its fuel so thoroughly that it can burn almost all of it, rather than only the fuel near its center. And it burns that fuel at such a gentle, unhurried rate that a single red dwarf can shine steadily for trillions of years, in some cases for many tens of trillions. This means that the red dwarfs forming today, and the ones that will form near the end of starbirth, are only at the very beginning of their lives. The universe is not yet old enough for a single red dwarf to have died of old age. Every red dwarf that has ever existed is still shining now, somewhere, and will go on shining for spans that dwarf the present age of the cosmos. Their deaths all lie in the future, far beyond the death of every larger star. Red dwarfs are also, quietly, the most common stars in the universe. They outnumber stars like the Sun by a wide margin. We do not notice this from where we stand, because they are so faint that the brighter stars outshine them and draw the eye. But in the far future, when the brilliant stars have all burned out, the red dwarfs will remain, and the universe will become, for an enormous span, a place lit almost entirely by their soft red light. The faint and overlooked stars of today are the lasting inhabitants of tomorrow. Picture the universe in this long red afternoon. The grand spiral galaxies are gone, their structure scrambled by mergers and faded with age into smooth, dim ellipticals. Star formation has ended. No new stars are being born anywhere. But scattered through these old, quiet galaxies, countless small red stars still glow, each one burning slowly through its long life. Any worlds that circle them are bathed in a steady, gentle, reddish light, neither growing nor fading, holding constant across spans of time longer than the entire previous history of the universe. There is a kind of peace in this picture that the bright early cosmos never had. The fierce, fast-living giant stars are gone, with their violent deaths and their brief, blazing lives. What remains is slow and steady and patient. The red dwarfs do not flare or explode. They simply shine, quietly and without drama, for almost unimaginable lengths of time. The universe has traded its brilliance for endurance, its fireworks for a long, low, constant glow. But even the most patient star must eventually exhaust its fuel. A red dwarf burning for tens of trillions of years is still burning toward an end. As it runs low, it does not erupt the way a massive star does. It contracts and cools quietly, shifting from red to a deeper, dimmer red, and finally settles into a small, dense remnant, a white dwarf, no longer burning at all, only radiating away its stored heat. One by one, across spans almost beyond writing down, the red dwarfs will follow this path. They will dim, contract, and go out, joining the slowly growing population of cold remnants in their dark galaxies. What lets a red dwarf live so long is the way it stirs itself. In a star like the Sun, only the fuel near the core is ever burned. The outer layers never mix down into the center, and so much of the star's hydrogen is never used. A red dwarf is different. It is churned all the way through by slow rising and falling currents, so that nearly all of its fuel is eventually carried down into the burning core and consumed. It wastes almost nothing. Combine that thoroughness with an extremely slow rate of burning, and you have a star that can shine, faint but steady, for tens of trillions of years. The worlds that circle these small stars would know a very different kind of day than ours. A planet warm enough for liquid water would have to huddle close to its dim red sun, close enough that it would likely keep one face turned always toward the star, one side in perpetual reddish daylight and the other in perpetual night. The light falling on such a world would be red, soft, and steady, never the brilliant white of our own noon. And it would last, unchanging, for spans of time longer than the entire age of stars that came before. Whatever the far future holds for life, if it holds anything, it may unfold most often in the long red light of these patient little suns. The early life of a red dwarf can be restless, marked by flares that flash out from its surface, but this is a feature of their youth. As they settle into their long maturity, they grow calm, burning with a steady, reliable light across spans of time that defy comparison. This is what makes them the true inheritors of the cosmos. The brilliant stars are a brief extravagance, spending their fortunes in a few million years. The red dwarfs are the patient savers, drawing out their modest means across trillions. In the long account of the universe, it is not the bright and the fast that endure, but the dim and the slow. And then, at last, somewhere in the universe, the final red dwarf will exhaust the last of its fuel. It will dim and cool and contract, and its light will fade until it can no longer be seen. With that single fading point of red, the last true starlight in the entire universe is extinguished. No star is being born, no star is still burning. The age of stars, which has lasted from the first dawn of light through hundreds of trillions of years, finally comes to its close. The universe goes dark, not all at once, but with one last red ember quietly going out. Part 7. When the last star goes out. The death of the last star is the gentlest possible ending to the age of light. There is no explosion, no final catastrophe, no great event to mark the moment. There is only a single small red star, somewhere in some old and quiet galaxy, burning down the last of its fuel across an immense span of time, growing dimmer and dimmer until at last its light fades below the point where anything could see it. And then the universe holds no living star at all. It is worth dwelling on the scale of what has ended. From the first stars that lit the early cosmos to this final fading ember, the age of stars will have lasted on the order of 100 trillion years and more. That is the entire span across which the universe was full of light, across which galaxies turned bright with newborn suns, across which worlds formed and warmed, and, perhaps, came alive. All of it, the whole lit chapter of the cosmos, closes here with the quiet death of one small red star. After that moment, the universe is dark in a way it has never been before. The galaxies still exist, still hold their stars, but those stars are no longer burning. They are remnants now, the cooling corpses of stars that died long ago. The light that remains comes not from any fire still burning, but from stored heat slowly leaking away, the fading warmth of embers in a hearth where the flames have already gone out. The universe is living, from this point on, entirely on what it has already made. This marks the boundary between two great ages. Behind us lies the age of stars, the bright chapter we have just walked through, lasting 100 trillion years and feeling, from the inside, like forever. Ahead lies a far longer age, the age of remnants, in which nothing burns and the universe slowly surrenders its stored heat into the growing dark. By every cosmic measure, the age of stars was the brief part. What comes after is the long part, longer than the age of stars by amounts so large that the entire history of starlight becomes a thin, bright thread at the very beginning of the timeline. It is natural to feel something at the death of the last star. The image carries a weight, the idea of a universe that has lost its light forever. But it is worth holding the moment carefully, in its true proportion. The last star does not die soon. It dies after 100 trillion years and more, an unimaginable expanse of time in which countless generations of stars will have lived and died, in which worlds beyond counting will have formed and faded, in which whatever can happen in a universe full of stars will have had every chance to happen many times over. The light is not stolen. It is spent, fully and slowly, across spans we can barely conceive. And the darkness that follows is not empty in the way we might fear. The remnants are still there. The white dwarfs, the neutron stars, the cooling cores of dead stars, the scattered planets, the black holes left by the most massive stars, all of these remain, drifting through the dark galaxies. The universe has not been destroyed. It has only stopped making new light and begun the long process of letting its old warmth fade. The cosmos has entered its long evening, and the evening, as it turns out, lasts far longer than the day. It helps to set the proportions clearly because they are easy to lose. If the entire future history of the universe, all the way to the long cold, were compressed into a single year, then the whole age of stars, from the first dawn of light to the death of the last red dwarf, would occupy only the first few moments after midnight on the first day. Everything else, the cooling of the remnants, the unbinding of the galaxies, the long rain and slow evaporation of the black holes, would fill the rest of that year and far, far beyond. We live not merely early in the universe's story, but in the very first instant of its first morning. And yet the death of the last star, when it comes, is not really a loss in the way the word suggests. The light is not taken. It is spent, completely and slowly, across a span so long that everything a universe full of stars could ever do has been done, countless times over, on countless worlds. Every sunrise that could happen has happened. Every warmth that could be given has been given. The age of stars does not end because something fails. It ends because it has been lived all the way to the end, fully and without waste, and what follows is simply the long, quiet evening that every long day earns. What lies on the far side of this boundary is not nothing, only a different kind of something. The galaxies are still there, holding their stars, but the stars no longer burn. They are remnants now, glowing only with stored and fading warmth. The universe has not been emptied so much as it has been hushed, its fires banked, its loud and luminous youth given over to a long and quiet maturity. The age of remnants is darker than the age of stars, and far longer, but it is not a void. It is the cosmos living on its memories, on the warmth of fires that have gone out, for spans of time longer than the burning ever lasted. So we step across that boundary now, from the age of stars into the age of remnants, from the chapter of fire into the chapter of cooling embers. The galaxies are dark, but they are not yet cold. The remnants still hold the heat of the stars they once were, and for an enormous span of time, that fading warmth will be the only light the universe has left. We turn now to those embers, to the long, slow cooling of everything the stars left behind. Part 8. The Era of Embers. With the last star gone, the universe enters the long age of remnants, sometimes called the degenerate era. The galaxies, now dark, are populated not by living stars, but by their remains. White dwarfs, the exposed cores of dead stars, drift through the gloom, slowly radiating away their stored heat. Neutron stars, even denser remnants, cool quietly in the dark. Failed stars called brown dwarfs, which never grew massive enough to truly ignite, persist as dim warm bodies. Scattered planets, torn from their dead stars, wander alone. And black holes, the remains of the most massive stars, wait in the dark for a story that comes much later. The defining feature of this era is that nothing new is being made. There is no more fusion, no more burning, no more fresh energy entering the universe. Everything that happens from here on is powered by stored warmth, the leftover heat of stars that died long ago. The universe is like a great house in which the fires have all gone out, lit now only by the fading glow of embers in the grates. For a time, there is still light, but it is borrowed light, leaking slowly away, with nothing to replace it. A white dwarf is a useful thing to understand here, because it is the most common remnant, and it tells the story of this whole era in miniature. When a star like the Sun dies, it sheds its outer layers and leaves behind its core, a sphere about the size of the Earth but holding much of the mass of the original star. That core is not burning. It holds no fuel. It is supported against its own crushing gravity by a strange quantum pressure, the resistance of its tightly packed electrons, which keeps it from collapsing further. And it is hot, glowing white with the leftover heat of the star it once was. From the moment it forms, a white dwarf does only one thing. It cools. It radiates its stored heat into space, very slowly, growing fainter and changing color as it goes. It shines white at first, then yellow, then orange, then a dull red, then a faint warmth, visible only in infrared, then, eventually, nothing the eye could ever catch. This cooling takes an enormous span of time, far longer than the present age of the universe. A white dwarf forming today would still be glowing faintly, somewhere in the dark, long after the last ordinary star has died. The neutron stars cool too, in their own way, these remnants so dense that a spoonful of their material would outweigh a mountain. They begin extraordinarily hot and slowly surrender that heat to the dark, fading across spans of time, as long as the white dwarfs or longer. And the brown dwarfs, the stars that never quite were, give off their faint warmth and slowly cool as well, joining the general fading of everything that holds heat. Across the dark galaxies, every remnant is doing the same patient thing, letting go of its warmth, into the growing cold. It is not a completely lightless era, at least not at first. Rare events still produce brief flickers. Two white dwarfs, drifting through a dark galaxy, may occasionally pass close enough to fall together. If they collide or merge, they can briefly blaze, releasing a flash of light into the dark before fading again. Such events grow rarer and rarer as the era goes on, and the remnants spread further apart. But for a long time, they are the universe's only fireworks, occasional and faint, scattered impossibly far across the gloom. A galaxy in this era would be dark almost everywhere, lit now and then by a single distant flare that quickly dies away. The cooling of these remnants is so slow that it is hard to find a comparison for it. A white dwarf forming now, at the death of a sun-like star, will still be glowing faintly tens of billions of years from now, and will not finish cooling for far longer still, long after the last ordinary star has died. The remnants are not racing toward darkness. They are easing into it, surrendering their warmth so gradually that across spans dwarfing the present age of the universe they barely change. The era of embers is patient beyond any human measure, a cooling so gentle it would seem from inside any single age to be standing perfectly still. Even in this dark era, the universe finds occasional ways to make a little new light. Two of the failed stars called brown dwarfs, drifting through a dead galaxy, may now and then collide and merge, and if their combined mass is just enough, they can ignite into a genuine small red star, a new ember kindled long after starbirth was thought to be over. Such events are extraordinarily rare, scattered across enormous spans of time and space, but they mean the galaxies are never quite perfectly dark, not for a very long while. Here and there, across the gloom, a chance collision lights a small new star that burns for a while and then, like all the others, fades. The image of a house lit only by embers is worth holding, because it captures the feeling of this era exactly. The great fires are out. No new flame will be struck. But the embers still hold a gentle warmth, and they give it up slowly, glowing fainter and redder as the long night settles. Anyone moving through such a house would find it dim but not yet dark, warm but cooling, full of the quiet evidence of fires that burned brightly not so long before. The era of embers is the universe in just this state, its hearths cooling, its light failing gently, the warmth of vanished stars slowly seeping away into a dark that has all the time in the world. The era of embers is long, far longer than the age of stars that preceded it. For span after span, the remnants drift and cool, the galaxies grow darker and colder, and the universe settles deeper into its evening. There is no urgency here, no crisis, only the slow and steady surrender of heat. The cosmos is winding down the way a warm room cools after the fire is out, gradually, evenly, without alarm. And as the embers cool toward the temperature of the surrounding dark, they approach a final resting state, a condition in which they give off no light at all. The white dwarfs are becoming something new, something the universe has never held before, because there has never yet been time enough to make one. They are becoming the cold, dark stars, the cinders that no longer shine. Part 9. The stars that never shine. Given enough time, a cooling white dwarf finishes its long surrender. It radiates away the last of its stored heat, drop by immeasurable drop, across spans of time so long that the present age of the universe is nothing beside them. And when the last of that warmth is gone, when the white dwarf has cooled all the way down to the temperature of the surrounding dark, it becomes something new. It becomes a black dwarf, a cold, dark, dense sphere of crystallized matter, the mass of a star compressed into the size of a world, giving off no light at all. Here is one of the most quietly remarkable facts in all of astronomy. No black dwarf exists anywhere in the universe yet. Not one. The cooling of a white dwarf takes so enormously long that, in the entire history of the cosmos so far, not a single white dwarf has had time to finish the process. The universe is simply too young. Black dwarfs are stars of the future, a population that cannot appear until long after the last living star has died, when the oldest white dwarfs have at last cooled into darkness. They are a kind of object the universe has been preparing for billions of years and has not yet been old enough to make. When black dwarfs finally do appear, in the long age of remnants, they will fill the dark galaxies with invisible cinders. Each one is the cold, permanent remains of a star that once burned, the final resting state of ordinary matter once all its heat has fled. A black dwarf is not destroyed, and it is not gone. It is simply finished, holding its mass and its shape in the dark, neither burning nor cooling further, because there is no warmth left in it to lose. It has reached the same temperature as everything around it, and so it rests. The interior of a black dwarf is a strange and quiet place. As a white dwarf cools, the matter inside it is thought to crystallize, its atoms settling into a regular, rigid lattice, a single enormous crystal the size of a planet. The material is mostly carbon and oxygen, the ash of the fusion that once powered the star. So a black dwarf is, in a sense, a world-sized crystal of carbon, dark and cold and dense, the diamond remains of a star that shone for billions of years and then went out. It is a beautiful image, and a still one. Our own sun is bound for this fate. In about 5 billion years it will swell, shed its outer layers, and leave behind a white dwarf, a small hot ember about the size of the Earth. That ember will then begin the long cooling, glowing white, then yellow, then red, then dimmer and dimmer across spans of time beyond imagining. And at last, in the far future, the remains of the sun will cool into a black dwarf, a cold, dark crystal drifting through whatever is left of the merged galaxy, giving off no light, holding the last of the matter that once warmed the Earth. The star that lit our world will end as a quiet cinder in the dark. There is something deeply restful in the black dwarf, even though it is, in a sense, the corpse of a star. It is not violent. It is not in crisis. It has simply reached the end of its long cooling and come fully to rest. The whole drama of the star, its birth from collapsing gas, its long burning, its swelling and shedding, its slow fading, has finally resolved into this single still state, a cold sphere that asks nothing and changes no more. The universe, in the black dwarf, has found one of its quietest possible endings for matter. The crystallization inside a cooling white dwarf is a real and gradual process. As the remnant loses heat, its tightly packed carbon and oxygen begin to settle from a churning fluid into a solid, ordered lattice, starting at the center and working slowly outward. Over an enormous span, the whole interior stiffens into a single rigid crystal, a structure of almost unimaginable density and regularity. By the time it has cooled fully into a black dwarf, the remnant is essentially one continuous crystal the size of a planet, dark and cold and still, holding within it the settled ash of all the fusion the star ever performed. It is worth pausing on what this means for our own sun, and for the Earth it warms. The atoms that make up our world, the carbon and oxygen and iron, were forged in earlier stars and gathered into the cloud that became the sun and its planets. Far in the future, the sun's own remains will cool into one of these cold crystal cinders, carrying within it the matter that once shone down on every living thing. The light that warms us now will end as a dark and silent crystal, drifting through the remains of a galaxy that has long since stopped making stars. It is a quiet ending for a star, and a strangely gentle one. And it is the ending that waits, in time, for nearly every star the universe has ever made. The brilliant ones leave behind denser remnants, and a rare few leave black holes, but the great majority of stars, the countless ordinary suns, are bound for exactly this fate, a slow cooling into a cold, dark crystal adrift in the dark. The black dwarf is not a strange exception at the end of the timeline. It is the common destiny of starlight, the place where most of the light the universe has ever made finally comes to rest. A black dwarf keeps no record of the long life that made it, and yet it is nothing but that life's remains. Every atom in it passed through the burning core of a star, was forged or rearranged in the heat of fusion, and is now held cold and still in a crystal that will not change again. In a sense, the black dwarf is the most honest object in the universe, a thing reduced entirely to what it is, with no fire left to perform and nothing left to spend. It simply exists, cold and complete, the final and most patient form that ordinary matter can take once all its warmth has been given back to the dark. But the black dwarfs are not truly the end of the story, only a stage in it. They mark the resting state of ordinary matter once its heat is gone, but the matter itself remains, locked in those cold crystal spheres. What happens to it next depends on processes that act over spans even longer than the cooling of a white dwarf, processes that touch the very building blocks of matter, and that may, over time, beyond all counting, undo even these patient cinders. Before we follow that thread, though, there is a larger change taking place around the black dwarfs, a change not in the remnants themselves, but in the galaxies that hold them. For even as the stars cool into darkness, the great structures they belong to are quietly coming apart. Part 10. The slow unbinding of the galaxies. Galaxies seem permanent to us, these grand wheels of stars that have turned for billions of years and look as though they might turn forever. But they are not permanent. Over spans of time far longer than the age of stars, a galaxy slowly comes undone, its members scattered and swallowed, until the structure that once held hundreds of billions of stars has dissolved into the dark. The unbinding of the galaxies is one of the great slow processes of the far future, and it works through nothing more than gravity and time. The mechanism is subtle. Within a galaxy, the stars and remnants are constantly moving, circling the center, passing one another at a distance. Now and then, two of them pass close enough for their gravity to tug noticeably on each other, exchanging a little energy as they swing by. In any single encounter, the effect is tiny. But across enormous spans of time, with countless such encounters happening throughout the galaxy, the small exchanges add up. Some remnants gain energy from these gravitational near misses and are gradually flung outward, eventually escaping the galaxy entirely, drifting off into the growing emptiness between the islands of the cosmos. Others lose energy and sink slowly inward, spiraling down toward the galaxy's center. At the center of nearly every large galaxy lies a supermassive black hole, an object millions or even billions of times the mass of the Sun. Our own Milky Way holds one at its center now. In this far era, as remnants spiral inward through the slow gravitational shuffle, many of them eventually reach that central black hole and are swallowed, adding their mass to it. The central black hole grows, feeding on the infalling remains of the galaxy's stars, while the outer remnants are slowly evaporated away into intergalactic space. The end result, given enough time, is that the galaxy dissolves. Most of its dead stars are flung out into the dark, scattered across volumes that keep on growing as the universe expands. A fraction fall to the center and are absorbed by the supermassive black hole. The graceful structure of the galaxy, its concentration of stars, its bound and turning form, comes apart, leaving behind isolated remnants drifting alone and a single, massive black hole where the center used to be. The galaxy is reduced to its darkest, simplest essentials. This process is unimaginably slow. It unfolds over spans far longer than the 100 trillion years of the age of stars, far longer even than the cooling of the white dwarfs into black dwarfs. Structure that appears utterly permanent to us, the very shape of a galaxy, is on these timescales only temporary, a passing arrangement that gravity and time will eventually dismantle. The cosmic web itself, the great pattern of filaments and voids, loses its meaning as the galaxies unbind and their contents scatter or fall inward. Picture the universe after this has run its course. The galaxies, as gatherings of stars, are gone. What remains, spread across enormous and ever-growing distances, are isolated objects drifting alone in the dark, cold black dwarfs flung out from their dissolved galaxies, scattered neutron stars, wandering planets, and here and there, the supermassive black holes left where galactic centers used to be. Each object is separated from the next by distances that keep on widening as space expands. The universe has become a thin scattering of cold remnants and dark giants, drifting apart in a growing emptiness. The timescales of this unbinding are difficult to hold beside the ones that came before. Stars die in millions to trillions of years. White dwarfs cool across far longer spans still, but the gravitational evaporation of a whole galaxy works on a timescale longer yet, a span across which countless near misses must accumulate before the structure finally comes apart. Each individual encounter changes almost nothing. It is only the patience of the process, the sheer number of slow gravitational tugs across an almost endless stretch of time, that eventually scatters a galaxy's stars to the dark and drops the rest into the central black hole. A remnant flung outward in this way faces a strange and lonely future. Once it escapes its galaxy, it drifts into the widening emptiness between the islands of the cosmos, where there is almost nothing, no other star, no structure, no light. And because the universe is expanding, the space around it keeps on growing, carrying it ever further from anything else that remains. These ejected cinders become the loneliest objects in all of creation, cold, dark spheres adrift in an emptiness that has no edge and no neighbor, falling away from everything else forever. The unbinding of the galaxies does not gather things together. It scatters them, gently and finely, across an emptiness that only ever grows. It is humbling to realize that the galaxies, which seem the very emblems of permanence, are only passing arrangements. The Milky Way looks as though it has always turned and always will, but it is held together only loosely by gravity working across enormous distances, and gravity that binds can also, given enough time, scatter. A cross spans far longer than the age of stars. The slow exchange of energy among its members will undo the galaxy entirely, flinging most of its remnants to the dark and dropping the rest into the center. Nothing the universe builds is exempt from this. Everything structured is temporary, and only the simplest things, in the end, endure. It is a quiet picture, and an orderly one. Nothing has been destroyed in violence. The galaxies have not been shattered. They have simply relaxed apart, their members going their separate ways across spans of time we can barely write down. The universe is not coming apart. It is spreading, thinning, simplifying, shedding its structure the way a long exhale releases the last of its breath. And among the things that remain, The supermassive black holes are about to take center stage, for as the remnants scatter and the galaxies fade, the universe is entering an age in which the black holes are nearly all that is left. But first, there is a question to face about the cold remnants themselves, about whether even they can last forever, or whether the matter they are made of has an ending of its own. Part 11. If matter itself should fade. There is a question at the foundation of the far future that we cannot yet answer, and it concerns the stuff that everything is made of. Ordinary matter is built from atoms, and atoms are built from a small set of particles, among them the proton, which sits at the core of every atom in your body and in every world and star. The proton has always seemed perfectly stable, perfectly permanent, the kind of thing that simply lasts. But some of our best ideas about physics suggest that it may not last forever. They suggest that the proton, given enough time, very slowly decays. If protons do decay, they do so on a timescale almost beyond comprehension. The average lifetime of a proton, if it has one at all, would be staggeringly long, far longer than the present age of the universe, far longer even than the age of stars. A proton might wait through spans of time so enormous that the whole bright history of the cosmos passes in what is, for it, the blink of an eye. But if it does eventually come undone, releasing its substance as lighter particles and radiation, then the consequences for the far future are profound. For it would mean that ordinary matter is not eternal. It would mean that everything built from atoms has, written into it, a slow and certain ending. Follow that thread forward, and the cold remnants of the universe take on a different fate. The black dwarfs, those world-sized crystals of cooled matter, would not rest forever. Atom by atom, across spans of time beyond all counting, their protons would decay, and the crystals would very slowly evaporate from within, their substance dissolving into a thin drizzle of light particles and radiation. The neutron stars would dissolve as well, and the scattered planets, and every other object built from ordinary matter. The solid relics of the universe, the patient cinders left by the stars, would quietly come undone, fading into the growing dark. What would be left, if matter decays, are the particles that the decay produces, and the objects that are not made of ordinary atoms at all. The black holes, which are not built from protons in the ordinary sense but are regions of pure gravity, would remain untouched by this slow dissolution. So proton decay, if it happens, clears the stage of cold remnants and leaves the black holes standing alone as the last large objects in the universe, surrounded by an ever-thinning haze of the particles that the decaying matter has released. It must be said plainly that we do not know whether protons decay. No one has ever observed it happen. Enormous and patient experiments have watched great volumes of matter for any sign of a single proton coming apart, and they have seen none. All this tells us is that if protons decay at all, their lifetime must be at least staggeringly long, longer than the most patient experiment could catch in the brief span of human history. Whether they decay on some still longer timescale, or whether they are truly and perfectly stable, remains one of the genuine open questions of physics. This uncertainty does not weaken the story of the far future, it deepens it. If protons are perfectly stable, the cold remnants persist for spans even longer than the rest of the timeline, and the universe's late history is slower and quieter still, a long age of cinders that simply endure in the dark. If protons decay, the remnants slowly evaporate, and the universe simplifies sooner toward its black holes and its thinning haze. Either way, the long direction is the same, toward a darker, emptier, colder cosmos. The two paths differ only in how patient the ending is. The idea that protons might decay comes from our attempts to unite the forces of nature into a single description. In several such theories, The apparent permanence of the proton is only an approximation that holds across spans of time so long that we have never had a chance to see it fail. If those theories are right, then even the most solid matter, the rock of a dead world or the crystal of a black dwarf, is very slowly unstable, its protons waiting through almost endless time before, one by one, they come apart into lighter particles and a flash of radiation. It would mean that nothing built from atoms is truly forever. To look for this almost impossibly rare event, physicists have built great tanks of ultra-pure water far underground, shielded from everything that might confuse the search, and watched them patiently for the faint signal of even a single proton coming undone. Across years of watching enormous volumes of matter, they have seen no such event. This does not prove that protons never decay. It only sets the bar of their possible lifetime even higher, far beyond the present age of the universe. The proton keeps its secret, and so the far future holds two possible shapes, one in which matter slowly evaporates and one in which it endures, with no way yet to know which is true. Whether or not the proton decays, the lesson of this chapter is the same. The far future keeps some of its answers hidden from us, and that is part of its character. We have traced the universe forward with remarkable confidence through the death of stars and the scattering of galaxies. And here, at the question of whether the very substance of matter lasts forever, our knowledge thins to honest uncertainty. There is no shame in that, and no cause for unease. The universe is under no obligation to reveal its last secrets to a species reading them from so near the beginning of time. Some doors it leaves open, and we may simply rest in the not knowing. There is something fitting in the fact that the far future keeps this secret from us. We have traced the universe forward through the death of the stars and the unbinding of the galaxies. And here, at the question of whether matter itself endures, the science reaches a place where it cannot yet see clearly. The proton holds its answer close. And so we carry the uncertainty forward gently, as one of the things the universe has not yet told us, and turn to the objects that remain standing in every version of the story, the dark giants that outlast the stars, the remnants, and perhaps even matter itself. We come now to the age of the black holes. Part 12. The Age of Black Holes. After the stars have died, after the remnants have cooled and scattered, after ordinary matter has either dissolved or been swept into the growing dark, the universe enters an age that belongs to the black holes. They are, by this point, the only large objects left. From the modest black holes that were once the cores of the most massive stars, to the supermassive giants left behind where galaxies used to turn, the black holes inherit a cosmos emptied of nearly everything else. This is the black hole era, and it is one of the longest and strangest chapters in the whole history of the universe. A black hole is a place where gravity has become so strong that nothing can escape it. Not matter, not light, nothing at all that crosses its edge, the boundary called the horizon. From outside, a black hole appears as a sphere of perfect darkness, a region from which no light returns, set against a sky that is itself growing dark. It is not a thing in the ordinary sense, not made of any surface or substance you could touch. It is a region of space so deeply curved by concentrated mass that it has closed itself off from the rest of the universe. In this era, the black holes are extraordinarily far apart. The unbinding of the galaxies scattered them across enormous distances, and the ongoing expansion of space carries them further from one another with every passing age. Each black hole drifts essentially alone, separated from its nearest neighbor by gulfs of emptiness that keep on widening. There is almost nothing left between them, only the thinnest haze of stray particles and stretched, faded light. The universe has become a scattering of dark spheres, drifting apart in a growing and lightless emptiness. For an enormous span of time, the black holes simply persist. They do not burn. They have no fuel. They do not cool in the way the remnants did, because they were never holding starlight's heat to begin with. They wait, holding their concentrated mass, the last great landmarks in a universe that has shed almost everything else. If there were anyone left to see, the black hole era would appear utterly still, a few dark giants hanging motionless in an endless dark, with nothing happening between them across spans of time beyond all imagining. It is worth sitting with how empty and how quiet this age is. The galaxies are gone. The stars are gone. The cold remnants are gone, or going. What remains is so spread out, so dark, so far between, that the universe of the black hole era would seem, to any observer, almost entirely featureless. And yet it is not eternal, even now. The black holes feel permanent, and for an unimaginable span they nearly are. But they hold a secret that will, in the end, undo even them. For a black hole, it turns out, is not perfectly black, and not perfectly permanent. Very slowly, across spans that dwarf everything that has come before, even a black hole leaks away into the dark. The isolation of the black holes in this era is almost beyond picturing. By now, the expansion of space has been at work for spans of time longer than every previous chapter combined, and the distances between objects have grown to match. A black hole drifting in the black hole era is separated from its nearest neighbor by an emptiness so wide that light itself, crossing at its full speed, would take spans beyond all counting to bridge it, if it could bridge it at all. Each dark giant is, for every practical meaning of the word, entirely alone, the sole feature of its own enormous and lightless region of the cosmos. And these are the last things the universe ever builds. Through all the ages we have walked, the cosmos went on making structure, stars, and worlds, and galaxies and clusters, ever more elaborate arrangements of matter and light. The black holes are the final term in that long sequence, the simplest and most enduring structures of all, the last landmarks left standing after everything more intricate has faded. They are not the universe's failure, but its last and most patient achievement, the dark monuments that outlast the stars, holding their ground in the growing emptiness for spans of time that make all of cosmic history before them seem brief. To stand, in imagination, in the black hole era is to stand in the quietest place the cosmos has yet become. There is no star to give light, no galaxy to give shape, no world to give a place to stand at all. Only a few dark spheres scattered across an emptiness, without edge or end. And yet there is a strange dignity in this age. The universe has not been ruined, it has been refined, stripped down across countless ages to its last and simplest landmarks. The black holes hold their quiet watch over a cosmos almost wholly at rest, the final guardians of structure in a universe that has nearly finished the long work of spreading out. This is the surprising turn at the far edge of the timeline. The objects that seem most permanent, the dark giants that have outlasted the stars and the remnants and perhaps even matter itself, are themselves on a timer, the longest and slowest timer of all. They are very gradually evaporating, giving off the faintest possible warmth, losing mass across spans of time so enormous that the whole previous history of the universe is brief beside them. The black hole era is long, longer than everything before it. But it is not endless. And the slow evaporation of the black holes is the universe's final great process, the last thing that will ever happen on the grand scale before the cosmos settles into its deepest and longest rest. We turn now to that slow fading, to the way even the black holes, given time beyond all counting, quietly disappear. Part 13. Even the black holes fade. A black hole is not perfectly black. This is one of the most unexpected discoveries in all of physics, and it changes the ending of the universe entirely. At the very edge of a black hole's horizon, in the restless quantum nature of empty space itself, a black hole very slowly gives off a faint warmth, the gentlest possible glow, and in doing so it loses, by an immeasurable trickle, a little of its mass. Across the long future, that trickle never stops. Drop by drop, across spans of time beyond all counting, a black hole evaporates. The glow is extraordinarily faint, far too weak to ever see. For a large black hole, it is colder than the coldest empty space around it. A warmth so slight, it is almost a mathematical whisper rather than a real light. And the larger the black hole, the fainter and slower this evaporation is. A black hole the mass of a star would take something like a 1 followed by 67 zeros in years to evaporate completely. The supermassive giants, millions or billions of times heavier, take far longer still, something on the order of a 1 followed by 100 zeros, a span of time so long it has its own name, a Google of years. These numbers are past holding in the mind, and that is part of their meaning. The black holes do not vanish on any timescale that connects to anything we know. They persist through the entire black hole era, seeming utterly permanent, while the universe around them grows ever darker and emptier and colder. For nearly all of its enormous life, a black hole barely changes at all, losing mass so slowly that across spans dwarfing the age of stars, it remains essentially the same. The evaporation is real, but it is patient beyond all comparison. There is a turn near the very end of a black hole's life, though. As it slowly loses mass, a black hole grows warmer and evaporates a little faster, and this feeds on itself. The smaller it becomes, the hotter it glows, and the faster it sheds what remains. So after an almost endless span of barely changing, a black hole spends the final stretch of its life shrinking and warming, with gathering speed, until in its last moments, it releases the last of its mass in a final burst of energy into the dark. After a Google of years of near-perfect stillness, the end, when it comes for any single black hole, is comparatively quick. One by one, across spans of time that make all the previous eras together seem brief, the black holes wink out. The smaller ones go first, after their long but lesser spans. The supermassive giants linger longest, the final great structures the universe holds, glowing with their almost non-existent warmth through ages beyond imagining. And then, at last, the largest black hole anywhere in the universe reaches the end of its long evaporation, brightens for its final moment, and releases the last of itself into the dark. With that, the universe loses its final landmark. The last definite object is gone. It is worth marking what this moment means. The evaporation of the last black hole is, in a real sense, the universe's last event, the final time anything definite happens anywhere in the cosmos. Before it, there were still objects, still places, still things that could be pointed to. After it, there is only the thinnest possible scattering of particles and stretched light, drifting apart in a darkness that has nearly stopped changing. The black hole era closes, after its Google of years, and with it closes the last age in which the universe held any structure at all. The faint warmth a black hole gives off arises from the restlessness of empty space itself. On the smallest scales, the vacuum is never perfectly still. It seethes with fleeting stirrings, pairs of particles that flicker into being and vanish again. At the very edge of a black hole's horizon, this seething is interrupted, so that now and then a particle escapes, carrying away a trace of the black hole's energy, while its partner falls within. To a distant observer, the black hole appears to glow, ever so faintly, and to lose mass by exactly that much. It is not light in any ordinary sense, but a slow and inevitable leak written into the nature of the horizon itself. The strangest feature of this process is that it runs backward from everything our intuition expects. A large black hole is colder than a small one and grows colder as it gains mass. A small black hole is warmer and grows warmer as it shrinks. So a black hole does not settle toward a steady temperature the way a cooling ember does. It does the opposite. As it loses mass, it heats up, and as it heats up, it loses mass faster, in a slow runaway that takes nearly the black hole's entire lifetime to become noticeable, and then finishes in a comparatively brief final flourish. The dark giants do not fade evenly. They wait, almost unchanged, across a google of years, and then, at the very end, they go quickly. There is something almost gentle in that arrangement. For nearly the whole of its enormous life, a black hole asks nothing and changes not at all, simply holding its place in the dark while the universe empties around it. Only at the very close does it stir, and even then its ending is a brightening rather than a violence, a last release of warmth into a cosmos that has long since gone cold. The most patient objects in all of nature keep their patience nearly to the end and then let go. When the last black hole gives up the final fragment of its mass, the universe passes a threshold it will never cross back over. Before that moment, however dark and empty the cosmos had become, there was still an object in it, still a place that could be pointed to, still something that could be said to happen. After it, there is only the faint and ever-thinning haze of what was released, drifting apart in a dark that has nearly stopped changing. It is as gentle an ending as can be imagined for so grand a thing, the universe's last definite event, arriving not as a catastrophe, but as a single faint flicker, far off in the dark, with no one left to see it. This is the deepest reach of the timeline's events. From here on, nothing large remains to happen. The stars died long ago, the galaxies unbound, the remnants cooled and perhaps dissolved, the black holes evaporated. The universe has shed everything it ever built, layer by layer, across spans of time we can barely write down, and what is left is almost nothing at all, spread across almost everything. The cosmos has nearly come to rest. And so we step now into the final and longest condition of the universe, the state it has been approaching since its first moment, the long cold that waits at the end of everything. Part 14. The long cold. After the last black hole has evaporated, the universe enters its final state, the one it has been moving toward from the beginning. There are no stars now, no galaxies, no remnants, no black holes. There is only an extraordinarily thin haze of the most basic things. Particles of light stretched to enormous wavelengths, faint and cold. Lone particles drifting unimaginably far apart. The last stray remains of everything that ever was, spread so thinly across a space so large that the distances between them are almost beyond meaning. And that space is still expanding, still growing, carrying the last few particles ever further from one another, forever. This is the state physicists call the heat death, or maximum entropy, and the name can mislead because it sounds hot, and it is the opposite. The heat death is the coldest condition the universe can reach. Its temperature falls toward absolute zero, the lowest temperature there is, and keeps falling, never quite arriving, but always approaching. The word heat in the name does not mean warmth. It means that all the heat there ever was has been spread out so evenly, so completely, that none of it can ever flow or do anything again. The universe has not burned up. It has cooled down all the way, as far as cooling can go. To understand why this is the end, it helps to understand entropy, which is often called disorder, but is better thought of as evenness, the degree to which energy has spread out. Things happen in the universe because energy is unevenly distributed, because there is hot beside cold, dense beside empty, ordered beside disordered. A star shines because it is hot and space is cold, and heat flows from one to the other. Everything that has ever happened, every flow and every change, has been energy moving from where there was more of it to where there was less. And every such flow makes the universe a little more even, a little more spread out, a little closer to the state where no further flow is possible. The entire timeline we have walked tonight is the story of that spreading. The stars formed and burned and died, pouring their energy into the dark. The galaxies turned and unbound, scattering their contents. The remnants cooled, surrendering their heat. The black holes evaporated, releasing the last concentrated mass into the thinnest possible radiation. Step by step, across spans beyond counting, the universe has been smoothing itself out, spreading its energy as evenly as it can be spread. The heat death is simply the end of that process, the point at which the energy is as even as it can ever be, and nothing more can happen. In this final state, the few particles that remain are so far apart that they essentially never meet. There is no warmth to flow, no structure to form, no event to mark the passage of time. Time itself still passes, in a sense, but with almost nothing left to change, it loses nearly all its meaning. The universe simply continues, colder and emptier, and more spread out with each passing age, a calm so complete that it is hard to even call it an ending. It is more like a settling, a coming fully to rest, after a long history of motion and change. And this final state is, by an enormous margin, the longest chapter of all. The age of stars lasted 100 trillion years. The black hole era lasted a Google of years, and the long cold lasts longer than all of them put together, with no defined end at all. It stretches on and on, past every number we could write, a calm and lightless and nearly changeless condition that has no natural stopping point. If the universe has a single dominant state across the whole of its existence, it is not the bright age of stars in which we live. It is this, the long cold, the quiet, that comes after everything else is done. The long cold is bound up with one of the most basic features of nature, the reason that time seems to flow in one direction at all. We remember the past and not the future. A cup shatters but never reassembles. Warmth spreads from hot to cold and never gathers itself back. All of these everyday truths are expressions of the same law, that the universe moves from less even toward more even, from order toward the smooth spreading out of energy. The heat death is simply the end point of that one-way flow, the state in which the spreading is complete and there is no longer any difference left anywhere for time to act upon. And the cold of that final state never quite reaches the very bottom. The temperature of the universe falls toward absolute zero, the lowest temperature there can be, but it approaches it the way a falling number approaches a floor. It can draw nearer to forever, without ever touching. There is always a little residual warmth, stretched thinner and fainter with each passing age, never fully gone. So the long cold is not a frozen photograph, but an endless, almost motionless approach, the universe forever cooling toward a stillness it never perfectly attains, growing colder and emptier and quieter across spans of time that have no end at all. There is a temptation to read the long cold as the saddest of all possible endings, and it is worth resisting that reading carefully. Nothing in this final state has been taken by force. No fire consumed the universe, no collapse crushed it, no disaster befell it. It arrived here by doing only what it had always done, letting its warmth spread out and even itself, until at last the spreading was complete. The long cold is not the universe broken. It is the universe finished, come fully and finally to rest, holding still in a calm so total that nothing remains to disturb it. If there is an ending without violence anywhere in nature, this is it. It is natural to feel a heaviness at this point, looking at a universe so empty and so still. But it is worth holding the long cold in its true light. Nothing here has been destroyed in violence. There has been no catastrophe, no shattering, no sudden loss. The universe has simply spread out as far as it can, let go of all its heat, and come to rest. It is the most peaceful state imaginable, a calm so total that nothing disturbs it, nothing troubles it, nothing breaks it. The cosmos has not died in fire or in fear. It has quietly, across spans of time we can hardly conceive, fallen still. And in that stillness, far stranger than the cold itself, there remains one last question, the one the night has been carrying all along, whether even this is truly the end. Part 15. The other roads. The long cold is the most likely ending, the natural destination if the universe keeps expanding as it does now. But it is not the only ending the universe might have. The far future depends on how the strange outward pressure of dark energy behaves across spans of time we cannot yet measure, and on a few questions of physics we have not yet answered. So before we ask what might lie beyond the end, it is worth pausing on the other roads the universe might take, the alternative endings that remain quietly possible. One of these is called the Big Rip. It would happen if dark energy, the pressure driving the expansion of space, were to grow stronger over time rather than holding steady. If the outward push intensified without limit, then the expansion of space would eventually overwhelm gravity at smaller and smaller scales. First, the clusters of galaxies would be pulled apart, then individual galaxies, then solar systems, as space itself expanded faster than gravity could hold things together. Near the very end, in this scenario, even planets and then atoms would be torn apart as the growing space outran every force that binds matter. The Big Rip would come sooner than the long cold, a tearing rather than a fading. Our present measurements do not require it, but they cannot entirely rule it out. Another possible road is the Big Crunch, and it is, in a sense, the mirror image of the long cold. It would happen if the expansion of the universe was someday to slow, stop, and reverse, if dark energy weakened or turned around so that gravity regained the upper hand. Then everything that has been flying apart would begin to fall back together. The galaxies would draw inward, the universe would grow hotter and denser, and across immense spans of time, it could collapse back toward a single, dense, hot point, a kind of mirror of the beginning from which it came. Present evidence shows the expansion speeding up, not slowing, so a big crunch looks unlikely. But the long-term behavior of dark energy is not fully known, and so the possibility lingers at the edge of the picture. There is a stranger possibility still, drawn from the physics of the very small. It is the idea that the empty vacuum of space, which seems so settled and so stable, might not actually be in its lowest possible energy state, but might rest in a slightly higher one, like a ball settled in a shallow dip partway down a hill. If that were so, then somewhere, sometime, a tiny region could slip down to the true lowest state, forming a bubble of new and more stable vacuum, that would expand outward at nearly the speed of light, remaking the laws of physics as it spread. This idea, sometimes called vacuum decay, is highly speculative, and if it ever happens, it gives no warning at all. It is best held lightly, as one of the universe's deepest open questions, rather than as anything to fear. What unites these alternative roads is that they are all genuinely uncertain. We do not know, with full confidence, which ending the universe is bound for. The long cold is the most favored, the most natural outcome of what we observe. But the Big Rip waits as a possibility if dark energy strengthens, the Big Crunch as a possibility if it reverses, and vacuum decay as a remote strangeness underlying all of it. The universe has not yet shown its hand. The ending is so far away, so unimaginably distant in time, that the cosmos has not yet had to choose which road it will walk. What decides between these roads is the behavior of dark energy across enormous spans of time, and that is something we are only beginning to measure. By mapping how the expansion has changed over the history of the universe and how it is changing now, astronomers are trying to read whether that outward pressure holds perfectly steady or strengthens or weakens ever so slightly as the ages pass. A steady pressure points toward the long cold. A strengthening one opens the road to the Big Rip. A weakening one leaves a distant door ajar for the Big Crunch. The measurements are difficult and still uncertain, and so the question of which ending awaits remains genuinely open. It is remarkable that so grand a fate hangs on so subtle a quantity. The difference between a universe that fades, one that tears, and one that collapses comes down to the faint and gradual behavior of the emptiest space, a pressure too weak to feel in any room yet decisive across the whole of the cosmos and the whole of time. We do not yet know the answer, and we may not know it for a very long while. But the not knowing changes nothing about tonight. Whichever road the universe is walking, it is walking it so slowly that the choice lies an unimaginable distance ahead, far past anything that touches the warm and lighted present we live in now. The honest summary is that we stand before a handful of possible endings and cannot yet say which is ours. That might sound like a failure of knowledge, but it is closer to a kind of freedom. The universe has written several possible last chapters and has not yet shown us which one it will keep, and the choosing lies so unimaginably far ahead that it casts no shadow at all over anything we know. We are free to look at the whole menu of endings with calm curiosity rather than dread, the way one might consider the distant weather of a season that will not arrive for 1,000 lifetimes, knowing it changes nothing about the warmth of the present day. There is something restful in that uncertainty, rather than something to fear. The endings are all so distant that not one of them presses on anything we know or love. They are possibilities written into the far future of everything, to be settled across spans of time beyond all counting by the slow behavior of forces we are only beginning to understand. We do not need to know tonight which road the universe will take. We only need to know that every road is long, and that the morning we live in now lies a near infinite distance from any of these far-off ends. And whichever road it is, there remains, past the very end of it, one last gentle question. The question the thumbnail has been quietly asking all along, whether anything at all lies beyond the end. Part 16. Beyond the End. We have followed the universe all the way to its rest. We have watched the stars form and die, the galaxies merge and unbind, the remnants cool into cold, dark cinders, the black holes evaporate across a Google of years, and the cosmos settle at last into the long cold, the most even and most peaceful state it can reach. And now we come to the final question. the one the night has been carrying from the start. When the universe has reached its long cold, is that truly the end of everything? Or could something lie beyond it? Here the science grows speculative, and the honest answer is that we do not fully know. But the question is real, and several of its possible answers are taken seriously. Consider first that the stillness at the end may not be perfectly final. Even in the emptiest space, the laws of quantum physics allow for faint, random fluctuations, tiny stirrings in what looks like absolute nothing. In a universe at its long cold, change has all but stopped, but not quite absolutely. Across spans of time so enormous they make the heat death itself seem recent, these faint fluctuations could, in principle, briefly assemble small ordered things out of the empty dark before they dissolve again into stillness, is less than #0. 5# is greater than. The cold is profound, but it may never be perfectly, eternally featureless. Even at the farthest reach of time, the void may still quietly stir. Consider, too, the idea that an end could somehow become a beginning. Some who study these questions have wondered whether a universe that has spread out and cooled completely might come to resemble, in a precise mathematical sense, the hot and smooth state that a universe begins in. If that were so, then the long cold might not be a full stop, but a handing over, the faded end of one cosmos becoming, across unimaginable time, the seed of another, a new beginning rising, where ours had come to rest. Other thinkers have imagined the universe passing through repeated cycles, or new regions of space, quietly budding off and inflating into universes of their own. None of this is established. All of it lies at the edge of what we can think about clearly. But it raises a possibility worth holding gently, that the very end may not be a closing, but a long, long pause. We should be honest about how uncertain all of this is. These ideas about what lies beyond the end are not settled science. They are careful guesses at the frontier, where our understanding thins out the way the universe itself thins toward its rest. We do not know whether the long cold is truly forever, or whether something stirs beyond it. It may be a question that stays open for as long as there is anyone to ask it. But for the listener drifting towards sleep tonight, that openness is not a frustration. It is a kind of comfort. The story is so long, and its final pages so far away, and so uncertain that there is nothing in it to fear, and nothing we are asked to settle tonight. And so we gather the whole journey and let it come to rest. We have walked the entire length of time, from the bright present where the stars still burn, through the emptying sky and the death of the last star, through the cooling embers and the cold, dark cinders, through the unbinding of the galaxies and the long age of the black holes, to the final stillness of the long cold and the quiet question of what lies beyond it. And the thing to carry away from all of it is a sense of scale and of peace. Everything that has ever happened in human history, everything alive now, every life that has ever been lived, sits in the first soft instant of a story almost beyond measuring in its length. The idea that order might briefly stir out of the emptiness has a careful logic behind it. In a universe given truly endless time, even the rarest things, the faint quantum flickers of empty space, would have chance after chance to occur, and across spans beyond all counting, small ordered arrangements could assemble by accident before dissolving once more into stillness. Most thinkers regard such fluctuations as fleeting and strange rather than as any true rebirth, and there are good reasons to be cautious about them. But they make a quiet point worth keeping, that absolute, perfect, eternal nothingness may be harder to achieve than it seems, and that even the long cold may never be completely without stirring. In the end, what the far future asks of us is humility and offers us perspective. We are trying to see to the end of time from a vantage point near its very beginning, with minds shaped by a world of days and seasons and single human lives. That we can trace the story at all, from the first stars to the long cold and the faint questions beyond it, is itself remarkable. But the honest edges of our knowledge are part of the gift. The universe does not hand us a tidy final page. It leaves the last chapter open, so far away and so uncertain that there is nothing in it to disturb a single quiet night, and everything in it to make the warm and lighted present feel like the rare and precious thing it is. And so the night comes around to where it began, but gentler now. We set out to ask what happens at the very end of the universe, and we have followed that question honestly, all the way to the long cold and the faint, uncertain stirrings that may lie past it. What we found at the end was not horror and not emptiness, but rest, a universe spread out and quieted and at peace, with a last door left softly ajar. There is no need to carry any of it with you now. The end is real, and it is gentle, and it is so far away that the whole of your life and the whole of the age of stars is gathered here in the bright and early morning of all things. The end of the universe, for all its strangeness, is not a wall rushing toward us. It is a slow softening, so unimaginably far away that our entire era, the whole age of stars in which we live, is only the morning of the cosmos. There is comfort in being early, in living now, while the stars still shine and the sky is still full of light. The long cold lies ahead, and it is real, but it is also so distant that all of time as we know it is gathered safely here in the warm and lighted present, which will last, by every measure, for a very, very long time. So let the whole long timeline rest now. Let the far ending wait where it belongs, at the end of everything, and let it trouble you not at all. The stars are still shining. The night is calm. Let your breathing slow, and let your thoughts settle, and let the long road wait. Sleep well, and good night.